Very good morning to all. I'm Dr. P. Gopinath, Assistant Professor, Selection Grade, Department of ECE, KIT, Kalaignar Karunanidhi Institute of Technology, Coimbatore. Today we are going to see the subject is B23 ECI 201 Circuit Analysis. In this circuit analysis, we are going to see the fourth unit. So that is a transient analysis. So in this transient analysis consists of and these are the topics that natural response, forced response, and transient response of RC, RL, and RLC circuits to excitation by basic standard signal, step signal, impulse signal, and exponential sources. Then complete response of RC, RL, and RLC circuits to sinusoidal excitation. So basically, what is meant by steady state? So steady state, it is a circuit having constant sources is said to be in steady state if the currents and voltage do not change with time. Ultimately, that is a constant source. Generally, we have called it as steady state. Then transient state. So that is a variation. That is a we have change. Some change is there. The behavior of the voltage and current when it is changed from one state to other state is called a transient state. So in this transient state having some time, that is a transient time, the time taken for the circuit to change from one steady state to another steady state is called transient time. So these are the basic quantities. Then generally natural and forced response should be defined. So how to define means natural response when we consider a circuit containing storage elements which are independent of the source. The response depends upon the nature of the circuit and is called the natural response. It depends on the type of element, their size and their connection. This response is independent of the source. So it is also known as transient response. Then forced response should be defined when we consider sources acting on a circuit. The response depends on the nature of the source or sources. This response is called forced response. Now we are going to see the first topic, that is a basic RL circuit. So in this RL circuit, resistor and inductor should be connected in series. Then voltage source we have denoted E. Then it should be connected switch, closed switch. Switch is closed at time t equal to 0. So in this circuit, current flow is there, that is I should be defined. Then apply KVL for loop for the above circuit. So that is a potential drop, that is also equal to potential rises. So E equal to ER plus EL. Then voltage across resistor ER, we have generally, we know that I into R. Then voltage across the inductor EL, that is equal to L into di divided by dt. It is an inductor. So this is equation number 1. Then equation 1 we have take Laplace transform for both sides. So we have converted E should be defined E divided by S taking Laplace. Then IR should be considered, that is a R into I of S plus L into S into I of S minus initial condition I of 0. We know that closing the switch, the current I of 0 equal to 0. We have substitute equation 2. We get current equation I of S. So I of S equal to E divided by S of R plus SL. Now taking partial fraction to obtain A and B values, we get the answer is I of S equal to E divided by RS minus E divided by R of S plus R divided by L. Now taking inverse Laplace transform on both sides, that is a I of S should be converted into I of t, that is equal to E by R minus E by R e power minus R divided by L into t. That is I of t equal to E by R. We have combined that, take outside E by R, 1 minus E power minus R divided by L into t. So this is equation number 3. Then current is said to rise exponentially So this is the plot we have obtained current versus time. In this initial state t equal to 0 state, then that is a maximum condition t equal to infinity. So we have achieved that is a E divided by R. Maybe that to determine the current at any time. Example, we have considered t1 time. Substitute t instead of t1. Then t equal to L divided by R. Then we substitute equation 3, that is I of t instead we have substitute L by R. So that is equal to E divided by R 1 minus e power minus R divided by L into L divided by R. So that value is e power minus 1. So e power minus 1 value is 0.3678. So that is a 0.632. That is 1 minus 0.63, sorry, 0.3678. That is 0.632 E by R. So we have obtained that is a final value for steady state condition 63.2 percentage. In this RL series circuit is defined as time during which the current increases to 63.2 percentage of its steady state value. Then based on voltage across resistance and inductance, equation should be defined ER equal to E of 1 minus e power minus R divided by L into T. Then similarly, voltage across inductor equation should be defined EL equal to e power minus R divided by L into T. Then now we are going to see the next one, the source free RL circuit. So already we have discussed that is a RL basic circuits. So now we are going to see the source free RL circuit. So in the source free RL circuit, we have defined the current flowing I equal to E by R. This is the circuit diagram. That is a resistor and inductor should be connected. Then current flow is there. Then here two switches. That is at t equal to 0. The switch is turned to position 2. Then which removes the source and puts a short circuit in RL series branch. Now this is the circuit diagram. We are applying KVL. So in this KVL, when switch S is in position 2 is the condition. So at the time, that is a voltage flow we have considered as 0. So that is 0 equal to I into R plus L into di divided by dt. The initial condition I of 0 equal to E divided by R. Taking Laplace transform on both sides, that is I of S R plus L into S of I of S minus initial condition I of 0, that is equal to 0. So we obtained I of S. So this is the condition E divided by R of 1 divided by S plus R divided by L. So this is the state waveform for t versus current, that is a time versus current equation. Then after taking inverse Laplace transform, I of t equal to L inverse of I of S. So I of S already obtained above equation. So substitute that and obtained I of t. So I of t equal to E divided by R e power minus R divided by L into t. Again at time t, it should be, that is a L by R should be defined, that is a time constant in second. Then t equal to L divided by R second, right? So I of t equal to E by R e power minus 1. So we have substituted e power minus 1 value, we know that 0.638, that is a 36.8 percentage of initial value we obtained. That is a time required to reach, that is a 36.8 percentage of the initial value. So in this percentage we have obtained source free RL circuit. In the source free RL circuit, that is a voltage source should be considered as 0. Here we have connecting two switches. That is a t equal to 0 at the time switch is turned to position 2. That is a condition. So here two switches, that is a two condition is there. That is a on condition is available. Then position should be changed. That is a that is main consideration for source free RL circuit. So based on that, we have seen the problem. A DC voltage of 100 volts is applied to a series RL circuit with R equal to 25 ohm. What will be the current in the circuit at twice the time constant? So here voltage value E equal to 100 volt is available, R value 25 ohm is available. So we know the condition I of t equal to E divided by R, 1 minus E power minus R divided by L into t. This time constant tau should be defined, that is a L by R. So here given t equal to 2 tau, that is I of t equal to 100 divided by 25 is the given value, 1 minus E power minus 2 tau divided by tau. So that is a tau tau cancel. Then 4 into 1 minus E power minus 2 is there. So E power minus 2 value, that is a 0.1353. So I of t equal to 3.45 ampere. So based on RL circuit, we obtain current value. Similarly, one more problem. In the circuit, that is here RL circuit is there. Find the expression for transient current after the switch is closed at t equal to 0, assuming 0 initial conditions. So here initial conditions also denoted that value is 0. So in this circuit, applying KVL, that is a first step. That is a 2 into I of t. That is a resistor should be defined. Plus, that is an inductor 5 into dI of t divided by dt. That is equal to 20. Taking Laplace transform on both sides. That is a 2 into I of s plus 5 into s into I of s minus I of 0. That is equal to 20 divided by s. Then given I of 0 equal to 0, because here assuming 0 initial condition. So 2 into I of s plus 5 into s into I of s, that is equal to 20 divided by s. So after minimization, I of s is 4 divided by s into s plus 0.4. Then taking partial fraction, obtained a and b value. So a and b value is 10 minus 10. Then next step, that is a final step, taking inverse Laplace transform. So inverse Laplace transform, that is a L inverse of I of s equal to 10 into 1 by s minus 10 into 1 divided by s plus 0.4. So these are the basic formula we are applying, that is a Laplace transform equation. So here it should be converted, the final equation I of t equal to 10 minus 10 e power minus 0.4 into t is the final answer for current value we have obtained based on the condition. Then you have see the one more problem. A series RL circuit with R equal to 30 ohm and L equal to 15 Henry has a constant voltage E equal to 60 volt. Applied at t equal to 0. Here assume condition circuit is there. Determine the current I. In this problem asking current I, the voltage across resistor and voltage across the inductor. Additionally asking. So this is the circuit diagram, solution of this problem applying KVL, that is a 30I plus 15 dI divided by dt. Then voltage value is there, that is a 60. As usual, taking Laplace transform, then after applying partial fractions, then and also consider for 0 initial condition, the current value I of s equal to 4 divided by s into s plus 2. Then taking partial fraction, a b value we have obtained. That is a value is 2, b value is minus 2. Then I of s equation is 2 divided by s minus 2 divided by s plus 2. Then taking inverse Laplace transform, that is a L inverse of I of s. So after taking inverse Laplace transform, 2 into 1 minus e power minus 2t ampere. So this type of problem asking current value is necessary one. Then additionally asking voltage across resistor and inductor. So we know the formula, that is a ER equal to I into R. So current value we know that the above equation we obtained 2 into 1 minus e power minus 2t into R value we have 30. So that is a voltage across resistor is 60 into 1 minus e power minus 2t volt. Then similarly voltage across inductor. So this is the formula EL equal to L into dI divided by dt. So EL equal to 60 into e power minus 2t volt. So this type of problem based on R RL circuits. Then next we are going to see that basic RC circuit. In this RC circuit diagram is there. Resistor and capacitor should be connected in series. That is a unit step driven RC circuit. This is the circuit diagram. Consider the RC series circuit with DC voltage applied through a switch. Then capacitance have an initial charge. So here resistor additionally that is a capacitor should be connected. So capacitor generally that is a initial charge of Q naught, that is a coulombs. Then initial voltage on the capacitor V naught equal to Q naught divided by C based on charge. Now we are applying as usual KVL. So resistor should be denoted I into R plus capacitor we have defined 1 by C integral I into dt plus V naught equal to that is a voltage source E. There is no initial charge Q naught equal to 0. That is a condition we have taken. So at the time IR plus 1 by C I into dt that is equal to E. The above integral equation may be solved by using Laplace transform. So next step is a Laplace transform. Taking both sides R into I of S plus 1 by C I of S divided by S that is equal to E divided by S. Then after minimization taking I of S equation, after taking inverse Laplace transform I of t equal to E divided by R into e power minus t divided by RC. Then I of t equal to initial condition t equal to 0, we obtain E divided by R. That is a 0 condition. Then I of t equal to t is the maximum limit infinity. So we obtain 0. So in this RC and RL, what is the difference means that is a maximum we have reached RL circuit that is a infinity. We obtained value is current value is E by R. But here R that is a RC circuit, it is opposite. So initial condition 0 itself we obtain E by R, then maximum limit we have apply like infinity value we are going to apply, we obtain 0 is the current value. So this is the waveform illustrate for I of t and t. The initial value of current is E by R amperes and the final value is 0 ampere. So in this voltage across resistor and voltage across capacitor we obtain. So this is the general formula ER equal to I into R, that's equal to E into e power minus t divided by RC. It is the equation for resistor. Then this is the equation for voltage across capacitor. That is EC equal to E into 1 minus e power minus t divided by RC. Right. Maybe EC increases with time when t should be infinity. That is EC is equal to the applied voltage and opposing it. The current I then becomes 0. The time constant tau equal to RC second. Then we obtain PR. So this is the equation E square divided by R e power minus 2t divided by RC. Then PC we have obtained E square divided by R e power minus t divided by RC minus e power minus 2t divided by RC. Then here capacitor. So the energy stored in capacitor is obtained by integrating PC from 0 to infinity. So this is the answer EC equal to that is we have taking integration with substitute the limit value, then 1 by 2 CE square. At the t value is RC second and I value is E divided by R e power minus 1. So maximum the same that is a 36.8% of initial current should be obtained. Hence, the time constant tau equal to RC second. So in this topic, we have covered that is RL circuits and based on problems. Then next one is a RC basics RC circuits. Okay, thank you.